Hi everyone, my name is Mani,
My name is Sarel.
and this is our motion planning project using global path planning with power law based TTC forces for collision avoidance. Uh, Before we actually start with the demo, I could just give you a small preface to the project and kind of mention how we came up with it. Basically, we started thinking about tower defense games and how the agents or the enemies in those games kind of move just mindlessly from their start goal to their or start to goal, and not really taking into the player's obstacle placement into account. So if the player placed like a turret along the way, the obstacles might just or the agents might will just die. They won't try to avoid them. So that's kind of our initial thinking process behind it. We kind of wanted to make a smart AI where they would avoid these obstacles. So while we were developing this project, we kind of had a dilemma between whether should we just actually make a game or we should probably go somewhere along the lines of making something that's more dynamic and something that feels a little bit more sandbox where users can interact with agents and kind of make their own map sort of thing, sort of like an asset store building project. Um, so we went with the latter, and to begin with, to go right off into like the algorithm, we again, as mentioned before, picked TTC because it was simple and or TTC with forces to be specific. And it was simple and it was easy to implement. But during the initial build, we just had an empty map. You see all the obstacles placed here. But before we just had like one or two agents, and it would be an empty world, and they would be going right at each other. And the TTC force would obviously make the agents avoid each other, but it was very jittery and it was very rigid. It was very jerky. Um, so after playing around with the bid, we decided to implement TTC forces using power law. And again, it was easy to use. We've already done it in project 2. And also it gives us more wiggle room because we're working with more parameters, so more options. Um, Unfortunately, after we implemented it, it was still not smooth. It was still quite jittery. So we contacted Dr. Ionis, and he said it could be because of the Unity time step and or the Unity's time dot delta time, because that's what we were using to calculate the forces. So that was one of the challenging parts in the project where we had to implement our own custom time step. And basically, we created a script where we pass in a custom time step of 0.05, and then we would pass in an update function where we would actually calculate the TTC force. Uh, that time step will basically prevent Unity from running its own time step and, uh, you know, to
Messing with our calculations.
yeah, it as Sarul just said, it messing with our calculations. So we got it to run a bit smooth. Then uh, again, we were still working on an empty world, not as dense as this one, where there are multiple pre-built objects. And for this, TTC didn't. It was okay, but it was still not perfect. So for that, we had to implement a global planner, and we used A star for that, with the Manhattan distance as our heuristics. And once I run quick this simulation, you'll see all the different nodes that will spawn, which will, yeah, these are all the different nodes of our A star, and you could see the path for each agents. Basically, this is the 8 agents simulation that we did in project 3, or project 2, my bad. And they'll be avoiding the agents using power law, but they'll be getting to their goals will be calculated using uh, A star. So they're moving quite slow. But you see this guy, there we go. They avoid each other. And if it's a head-on collision, they'll stop dead in their tracks and it'll be considered a dead agent. So I think,
So that agent, he was like basically pushed out of the way by the blue one.
yeah.
So the red one sort
So
of
he went out of the.
he basically collided with the tree. He was forced by the blue one to collide with the tree pretty much.
So that's that. Um, so the challenge, another challenging part about this was actually combining the local planner, which was our TTC, and the global planner, which was A star, combining it together in our custom-made planner. And Sarah will talk about that in our next scene that we have pulled up here, which gives more options for the user to play around with. Let me just pull it up real quick. Um, so here it is.
So as you can see, there's a lot more stuff going on in this scene. This is pretty much a sandbox where you can play around with all the different stuff that's there in our project. Um, Off the bat, you have like an agent which has a pre-computed A star path from here all the way up to here, and then the user is able to place obstacles with the use of his mouse. And let me just reset the level so I can show you how the agent behaves when you block his path. So let's observe what happens. Oh, there you go. The path has been updated. And then this happens like, dynamically, and it's really smooth. Is there some difficulty going through there, but then it should be fine. And then you path will be computed. So the way this works is we have an intermediate mid-level path planner that combines the global planner and the local planner. The way it works is in the beginning, it asks the global planner for the A star path, which is what you see here when you start the level. And then what it does is it feeds each waypoint on this path as a goal to the TTC power law. So in between these waypoints, it's using TTC to move. So it avoids naturally anything that comes in its way. Additionally, the mid-level planner also has functionalities which let it update the A star path dynamically. So the way that works is it's constantly looking a few steps ahead of its waypoints to see if any of them are in collision or not. So if I place it farther away, you can see that the path is not updated. But when it gets close, as in it's within its look ahead distance, it sees that one of its waypoints is in collision, and then it computes like a mini A star path from its current location to the next collision free point. So you can see this was the next collision free point, and it computed from the current position to that one. So this mini A star path is stitched back into the main path. So it's not like a huge recomputation. It's a very small recomputation, which makes it much more
So it's again,
efficient.
like you said, from the current node to the next node that's collision free.
Exactly.
So it's a small A star.
Right. And in addition to that, there's also stuff like, say if you block the agent off like this, he sort of wiggles out. So the way this works is that the agent is sort of pushed a little to the left or the right when he is stationary for too long. So this is in most cases enough to help get him, dislodged from any situations. But then there are cases where the agent will get trapped. Like let me trap the agent on purpose here. If I block off all his paths, you can see it's not quite easy. But yeah, I think now he should not have a way. Oh no, he does.
So TTC helped him to find a wiggle room
Yeah,
out of that sticky situation, and he was able to find a path.
but
Now he should be trapped.
yeah, now this should be too much trapped. Yeah, now the agent is trapped pretty much, and then he has nowhere to go. And then usually when the agent is trapped, the scripts are turned off. If they don't move, say within 5 seconds, if they haven't made any progress, then they're just turned off. So that's basically what this level is. You can play around with it. Oh, how can I forget? We can also change the precision with which our A star computes the paths. Basically, you manipulate the number of samples it takes. So right now in this scene, we are taking a lot of samples. So we don't really need so many. We can get away with something like this. So you can see there are a lot less samples, but then this is still really good. And you can also see that the samples do not appear where there are already obstacles. I can also show you this again by placing some more obstacles and recomputing the grid. So now when I recompute the grid, you can see that they no longer appear where the obstacles are. So that
You can
is,
go ahead and spawn a new agent.
oh
See
yeah,
how he acts.
yeah, let me
So
spawn.
you can spawn an agent as well, and their path is randomly generated.
Yeah, so his start node is probably somewhere here, so that's why he's making it. Okay, I think it's over here. Yeah, that's why he's making his way to the start node, and then from there he'll go all the way to his goal node. So we can spawn in a bunch of agents. There's also functionality to randomize their paths. Like if you hit D, then their paths change randomly. So let me clear all this away. Let's reset the level. So yeah, that's pretty much our project. Speaking of future work, we want to put this on the asset store as like a nice package with really usable APIs that people can just download and then just have a nice mini game up and running within few minutes. So that's pretty much it.
That's it. Thank you.
Thank you.